In this video, I will be discussing about the symmetries and conservation laws in physics in the context of Lagrangian mechanics. We know that for a system of n particles specified by small n generalized coordinates, where n is equal to 3n minus k is the number of holonomic constraints, we can write the Lagrange's equations of motion for the ith particle as d by dt of dou L by dou qi dot minus dou L by dou qi equal to 0. Here the index I can take values from 1 to n, then it will represent the whole system, the entire system. Remember, here I have considered only conservative systems so that I can express my force as a gradient of some scalar potential. There are such n equations of motion that are second order differential equations in T. Now if we solve this, we will have 2n integration constants. So these 2n integration constants have to be evaluated either from some initial conditions or from some boundary conditions. We need actually initial conditions of q's and q dots, generalized coordinates and generalized velocities, or we need some boundary conditions to determine this 2n integration constant. So obviously if we proceed in this manner, problem solving will become a tedious process. Now there are many situations in physics in which we cannot do the complete integration of this Lagrange's equation of motion. Actually this is not a necessity. Using some other ways we can get a great deal of information about the physical nature of the motion without even solving the Lagrange's equations of motion. So in fact we are interested in collecting these information rather than merely solving these equations of motion. So in many problems we can easily find out some relations or functions that can provide us valuable information about the system, and these relations are actually called first integrals of motion. And they are of the type f of q1, q2, q3 etc. up to qn, comma q1 dot, q2 dot etc. up to qn dot, comma t equal to constant. They are actually first order differential equations, and in fact various conservation laws such as conservation of linear momentum, angular momentum, conservation of energy that we are already familiar with in Newtonian mechanics are belonging to this first integrals type. Now we have already gone through cyclic or ignorable coordinates and seen that when a cyclic coordinate is present in a system, then the generalized momentum corresponding to that cyclic coordinate becomes a constant of motion. Now, if the generalized coordinate corresponding to a displacement along some direction is cyclic, then the translation of the system along that direction will not have any effect on the problem, will not make any difference to the problem. So in that case, we can show that corresponding linear momentum will be a conserved quantity. Similarly, if the generalized coordinate, if the cyclic generalized coordinate is a rotation coordinate, say some theta, then the rotation of the system about some axis through an angle theta will not make any difference to the problem. And in this case, the corresponding generalized momentum will be the angular momentum and it will be a conserved quantity. That means if a system possesses rotational symmetry about an axis, then the conjugate angular momentum will be conserved. Thus, it can be shown that symmetric properties of the system are closely related to the conservation laws. We will see them in detail. As a general case, we consider a system a closed system. So it's a closed system means it has no interaction with the surrounding systems. That is, it is completely isolated. There are n particles in the system and they are specified by n generalized coordinates q1, q2, q3 etc. up to qn. So for this system I can write the Lagrangian as L is equal to L of q1, q2, q3 etc. up to qn, comma q1 dot, q2 dot extra qn dot, comma t. Or simply in a more compact way, L will be a function of q, q dot and t. Now suppose the system has undergone some transformation. Let's say the system has been shifted to some distance, or say its orientation has been changed. Whatever be the transformation, the q's and q dots will now change, and consequently your Lagrangian will going to change. Now new Lagrangian, you can write it as L prime equal to L plus delta L, where delta is the variation in the Lagrangian. You know that L is a function of q, q dot and t. And for the moment, we assume that L does not depend on t explicitly. L does not depend on time explicitly. So we can write delta L as dou L by dou Qj into delta Qj plus dou L by dou Qj dot into delta Qj for some Qj. So what about this delta Qj dot? Delta Qj dot is nothing but d by dt of delta Qj. See, we mark this as equation number 1. Now, by Lagrange's equation of motion, we know that d by dt of dou L by dou Qj dot minus dou L by dou Qj equal to 0 implies dou L by dou Qj equal to d by dt of dou L by dou Qj dot. So we are going to substitute for this dou L by dou Qj in this expression in equation number 1. So equation number 1 will become delta L is equal to, instead of dou L by dou Qj, we will write d by dt of dou L by dou Qj dot. So d by dt of dou L by dou Qj dot delta Qj plus dou L by dou Qj dot into delta Qj dot. So this is actually, right side you have some derivation part which is in the form of some derivation of the product of some functions. Derivation of the product of two functions. So I can rewrite this thing as d by dt of dou L by dou Qj dot into delta Qj. If you expand this, you will get this. Okay, let's say this is first function, this is second function. Then if you expand this, you will get derivative of first function into second function plus first function into derivative of second function. Okay, so I am writing this thing in this form, and I am marking it as equation number 3. This is for the jth particle. Here I have considered only jth particle. For some Qj I have written this expression. Now for the entire system, I am going to put some summation. So the equation will be delta L is equal to d by dt of summation over j dou L by dou Qj dot into delta Qj. I am marking it as equation number 3. So this equation number 3 actually tells you is that whenever there is a change in Qj, your Lagrangian will go to change. Okay. Next we will discuss homogeneity of space and conservation law of linear momentum. This is what we are going to discuss first. Homogeneity of space and conservation of linear momentum. So here we consider the coordinate transformation in terms of translation. Suppose we displace or translate the system to some distance in space. Now if the physical properties of the system remain unchanged under translation, after translation, then we will say that the system possesses translational symmetry, which means space is alike everywhere for the system, and this is referred to as homogeneity of space. The statement under translation and symmetry physical properties do not change implies that Lagrangian of the system will not change. That is, delta L will become 0. Now equation number 3, which is d by dt summation over j dou L by dou Qj into delta Qj, which is nothing but delta L, will become 0. So we mark it as equation number 4. Here, since I am talking about translation, Qj is a Cartesian coordinate. Qj's are actually position coordinates. They have the dimension of length. So I am representing this Qj. Instead of Qj, I am going to write Rj. Okay. So I am considering jth particle in my system. Let's say my jth particle is initially at P, at the position P. Rj is its position vector. Now I have translated the system along the direction of n cap. Some direction, along some direction n cap. And this system has been moved through some distance epsilon. So this is an infinite symbol displacement. Now if you look at my jth particle, it is now at the position P prime. And let's say Rj prime is its position vector, where Rj prime is nothing but Rj plus delta Rj. This delta Rj is nothing but epsilon. Okay. So that means Rj prime, which is the position vector of the jth particle after translation, will be Rj plus epsilon. Now I am going to write this equation 4 as d by dt of summation over j dou L by, instead of qj I will write rj. So dou L by dou qj dot. So instead of dou L by dou qj dot, I have dou L by dou rj dot into delta rj equal to 0. Now what is this delta rj? Delta rj is nothing but epsilon, that infinitesimal displacement. Then this will become d by dt of summation over j dou L by dou rj dot into epsilon equal to 0. Now this epsilon is actually an arbitrary displacement which is independent of time, so I can take it outside this derivative part. So it will become epsilon into d by dt of summation over j dou L by dou rj dot equal to 0. So I am going to mark it as equation number 5. Now I have to evaluate dou L by dou rj dot. Dou L by dou rj dot. What is L? L is actually t minus v. So dou L by dou rj dot is nothing but dou t by dou rj dot minus dou v by dou rj dot. Here this dou v by dou rj dot will tend to 0 because we assumed that potential is dependent on position coordinate only. Potential is independent of velocities. We are actually considering only conservative systems. So dou v by dou rj dot will become 0. So finally you will get dou L by dou rj dot is equal to dou t by dou rj dot. Now what is t? T is half mj rj dot square. So do this derivation. Dou by dou rj dot of half mj rj dot square, which will give you half mj into 2 rj dot. Now the 2 will cancel and finally you will get dou L by dou rj dot, which is dou t by dou rj dot equal to mj rj dot. So this is mass into some velocity. So I am calling it as linear momentum of the jth particle Pj. So I have dou L by dou rj dot is equal to Pj. So I am going to substitute this in equation 5. I will get epsilon into d by dt of summation over j Pj equal to 0. Now what is this summation over j Pj? It is nothing but linear momentum of the entire system. P total, linear momentum of the entire system. So I have epsilon into d by dt of P total equal to 0. So epsilon cannot be 0. Of course, epsilon cannot be 0 because it is an arbitrary displacement. But d by dt of P total will be, should be 0 then. That implies P total will be a constant of motion. P total will be constant. That is linear momentum of the system. Linear momentum of the entire system will be a constant of motion. Thus, for a system possessing translational symmetry, linear momentum will be a conserved quantity. Next, we will discuss isotropy of space and conservation of angular momentum. So here we will look at the rotational transformation of the system. Here we allow the system to undergo some infinitesimal rotation and assume that its physical properties are not changing under rotation. That means its physical properties are the same in all directions. So this is what we called isotropy of space. Okay. Physical properties are not changing under rotation means delta L will become 0 here. Now the question is, if delta L equal to 0 for a system possessing rotational symmetry, what will be the quantity that is going to be conserved during motion? Okay, that we will find out. So here also I am considering the jth particle of the system, which is initially at the position P. Let Rj be the radius vector of this jth particle. Now let the system as a whole undergoes an infinitesimal rotation, say epsilon, about an axis n cap. Now, if you look at the jth particle, it got shifted to P dash. So the new radius vector will be Rj dash, which is equal to Rj plus delta Rj. But here delta Rj, you have to determine this delta Rj. So you can use this figure for that. So you can use this relation, angle is equal to arc by radius. Arc by radius. That means epsilon. Epsilon is the infinitesimal rotation. So epsilon is equal to delta R divided by Cp. Cp is the radius. So this relation you can use. Now how to find out Cp? If this angle is theta, then Cp is r sin theta. So you will get delta Rj is equal to Rj sin theta into epsilon. So I have put some direction here, n cap direction here, because infinitesimal rotation is a vector quantity. We consider it as a vector quantity. So therefore I am adding some direction to it. So we have delta Rj is equal to Rj sin theta epsilon n cap. So this I can be written as Rj cross n cap epsilon. Okay. Now equation 3 will be, or equation 4 will be, equation 4 is what? Delta L equal to 0. That means d by dt summation over j dou L by dou Rj dot into delta Rj equal to 0. So substitute for delta Rj, you will get d by dt of summation over j dou t by dou Rj dot Rj sin theta epsilon n cap equal to 0. Now dou L by dou Rj dot is nothing but dou t by dou Rj dot, which is equal to mj Rj dot. So you have d by dt of summation over j mg Rj dot n cap Rj sin theta epsilon equal to 0. So this is what. Now mg Rj dot is nothing but Pj, linear momentum of the particle. So finally you have summation over j n cap Pj Rj sin theta equal to 0. Here also we have taken the epsilon outside this bracket, outside this time derivative part, because it does not depend on time. So we have epsilon into d by dt of summation over j Rj cross Pj equal to 0. So this is nothing but Rj cross Pj. Now what is this Rj cross Pj? It is Lj, angular momentum of the jth particle. So finally you have epsilon into d by dt of summation over j Lj equal to 0. Now summation over j Lj is nothing but the total angular momentum of the system. So here again epsilon cannot be 0, but d by dt of summation over j Lj should be 0. That means L total should be a constant of motion. That means for a system possessing rotational symmetry, angular momentum is a conserved quantity. Next we will discuss homogeneity of time and conservation of energy. By homogeneity of time, we mean that system properties will not change with the time. So in this case, L will not depend on time t. That means dou L by dou t will become 0 in this case. Now the question is, what will be the conserved quantity here? Okay. So we know that L is a function of q dot and t. We also know that dou L by dou t equal to 0. So take the time derivative of this Lagrangian function. What you will get? dl by dt is equal to dou L by dou q into dq by dt, which is q dot. Then dou L by dou q dot into dq dot by dt, which is q double dot, and dou L by dou t. But it is 0, that we already know. So you have dl by dt is equal to summation over I dou L by dou qi into qi dot plus dou L by dou qi dot into qi double dot. Here also you can apply the Lagrange equation of motion, which is dou L by dou qi equal to d by dt of dou L by dou qi dot. So instead of dou L by dou qi, put this value, put this expression d by dt of dou L by dou qi dot. So finally you have dl by dt is equal to summation over I d by dt dou L by dou qi dot into qi dot plus dou L by dou qi dot into qi double dot. So again, this is the derivative. This is the derivative of some product of two functions. Derivative of the product of two functions. So you can write it in this way: d by dt of summation over I dou L by dou qi dot into qi. Expand this, you will get this. Now what is this dou L by dou qi dot? Dou L by dou qi dot is nothing but the linear momentum of the ith particle. So finally you have dl by dt is equal to d by dt of summation over I pi qi dot. Now take this dl by dt on the RHS and equate it to 0. You will get d by dt of summation over I pi qi dot minus L equal to 0. So obviously this quantity in this bracket will be a constant of motion. So you will get summation over I pi qi dot minus L will be a constant. We are going to call this constant as H. H is called Hamiltonian of the system. Okay. Now the question is, what is the significance of this H? What is the significance of this H? What is this Hamiltonian actually? So for that, we will start from here. We have H is equal to summation over I pi qi dot minus L. What is this pi? Dou L by dou qi dot. Now what is this L? L is actually T minus V. So substitute here, you will get dou T by dou L, dou qi dot minus dou V by dou qi dot into qi dot minus L. But here again, for conservative systems, dou V by dou qi dot will become 0. Then you will get summation over I dou T by dou qi dot into qi dot minus L as your Hamiltonian. So this is what you have. Now you know that T is nothing but half m q dot square. So dou T by dou q dot is nothing but m q dot. So q dot into dou T by dou q dot is equal to m q dot square, which is equal to 2 times the kinetic energy, 2T. So for this term, we are going to substitute 2T. So you will get H is equal to summation over I pi qi dot minus L is equal to 2T minus T minus V. That is equal to 2T minus T plus V, which is equal to T plus V. That is kinetic energy plus potential energy, which is nothing but the total energy of the system. So what you are actually getting for a conservative system, you are actually getting that Hamiltonian is nothing but the total energy of the system, and it will be a constant. So that's what homogeneity of time tells you. For a conservative system, total energy will be conserved. Always remember, if V is dependent on velocity terms, then this Hamiltonian will no longer become equal to this total energy of the system. Okay, so Hamiltonian will become the total energy of the system only for the conservative systems. So that's all about the symmetries and conservation laws. Actually, in this discussion, what we have seen is the connection between the symmetries and conservation laws. We have seen that for every symmetry, there is a corresponding law of conservation. This is the famous Noether's theorem. There are many versions for it. In a more simpler way, it can be stated that for each symmetry of the Lagrangian, there is a conserved quantity. For each symmetry of the Lagrangian, there is a conserved quantity, and this is exactly what we have learned in this session. Thank you.